So good afternoon, everyone. My name is Adriana Rivera. I'm a computer engineering student at the University of Texas at El Paso's Aerospace Center. So today I'll present on our work advancing ground station capabilities using a single web-based application for satellite tracking and communication. That is the outline that I will follow in today's presentation. So I'll start by giving a brief introduction about some concepts relevant to this discussion. We talked about CubeSats this morning. Reiterate, CubeSats are a class of nanosatellites. They're basically, each unit is 10 by 10 centimeters in size, which each unit weighing less than 1.3 kilograms. So they're pretty small satellites. And the fact that they're small makes them low cost and makes them have a short development period, which makes them attractive to a variety of sectors because it's a easier, cheaper way to prove concepts in space. So we at the Aerospace Center, we're currently working on a CubeSat mission called SleeperSat. This mission is scheduled to be launched in less than a year. The point is basically to prove the concept of rapid development of modular CubeSats. So in essence, you would be able to take any CubeSat module, plug it into another one, and they would be immediately able to communicate and work with each other in any configuration. In the development of this concept, we're also emphasizing digital engineering principles and techniques. So maintaining a digital thread of simulations, a digital twin is what we're trying to accomplish. What you see there is the model of our CubeSat. You can see it's a 2U robotic arm just plugged in like Legos to other 2 units. And in essence, they should be able to work together and communicate without any intervention from us. As part of this mission, we're also developing our own in-house ground station. The point is to automatically track and communicate with satellites operating in UHF and S-band frequency ranges. I'll go a little bit about why ground stations are important for CubeSat mission success. So just by the nature of CubeSats, they face some challenges, mostly due to their small size. So since you have a small surface area, you don't have that many places to put solar panels in, so you have a limited amount of power in the spacecraft. So you have to be very meticulous and manage your power well. So you might prioritize certain tasks over communication, etc. Another thing is that due to the size constraint, you might not be able to place antennas where you want to place them, where you have to be very specific or smart about where you place your antennas, because most CubeSats don't have a dedicated propulsion system to point the antenna towards the Earth or point the solar panels towards the sun to charge up, etc. So because we expect some difficulties from the CubeSat itself, we want to make the ground station portion of the communication link as strong as possible. And this is why we want to develop our own. The objectives of our application are to enable live satellite tracking, manage real-time communication, implement seamless UHF and S-band signal decoding, and provide real-time display of satellite data, all in a single application. And I say within a single application because some previous efforts that we made in the past to make this ground station work included running software on different machines or compatibility issues between Windows operating system and Linux and certain components that we wanted to use. So this time around, we want to make everything fit into a single program. So I'll go over the components of our system. The hardware components, of course, are antennas. You can see in the picture there, we use 2 cross-polarized UHF antennas, Yagi-Uda antennas, for our UHF communication, and they're mounted on our S-band dish. To move those antennas, we have an azimuth and an elevation rotor controller, and we mounted the antennas on top of each other so that we simplified the number of rotors that we needed. Also, as part of our hardware, we are using the USRP X300 software-defined radio. For software, you can see we have like a main ground station computer. It has a Linux operating system. We're also using a GNU Radio for our signal processing, and we're using a GPredict-based backend for our website, and of course, a server. I'll give a little bit of context about the communication setup in the spacecraft. So we're using a UHF transceiver, an S-band transceiver, a deployable UHF antenna, an S-band patch antenna, and the reason we're using 2 frequency ranges is to add another layer of safety. So if one fails, then we use the other one. For our modulation scheme, we're using QPSK. And as for communication protocols, we're using the AX.25 packet protocol. And we're using the ESTTC protocol. That's basically from our hardware provider, which is EnduroSat. So now I'll go about how we actually implemented the capabilities that we want into our website. So for the satellite tracking capabilities, we basically looked at the GPredict software, which is just a very popular open source satellite tracking application. We extracted all the graphical elements out of it, and we took just the computational code, which was basically just a TLE processor and the SGP4 orbital propagation model, and we formatted them in a website backend thing, like format. And how it basically works is the backend automatically fetches the most current TLE information for all active satellites from Celestrak every 24 hours. And then the user, through the graphical user interface, enters a satellite catalog number that they want to track. The backend searches for the TLE of that corresponds to that catalog number, and then it passes it through the SGP4 orbital propagation model, and then we get the following outputs that you see in the picture in real time. So the key outputs that we're looking for are the latitude and longitude, because we are plotting those in real time into a map, so we can visually see where our satellite is. We also get the azimuth and elevation values in case we want to move the antenna to follow the satellite. We get the velocity, and then one key component is we get the next AOS, acquisition of signal, which is just the date and time where the satellite will become visible to our ground station, and the LOS, which is when we're going to lose that communication window. GPredict also does the Doppler shift correction to it for us. So we basically just get the corrected frequencies. So now that we have those outputs that we need, we can go ahead and schedule the communication windows so that our antenna moves automatically without us having to manually move it, and we can establish that communication. So since we now know when the satellite is going to be passing over us, sometime before we can start moving the hardware so that it establishes that link with as much precision as possible. And we basically send the live azimuth and elevation values through a serial link to the communication, from the computer to the rotor controller. And so this is a part of the project that we're currently working on. So this is like work in progress or future progress. Like I said, we're using the USRP X300, and we added 2 160 megahertz daughter boards to basically cover the frequency ranges that we want, UHF and S-band. And then how we're planning to integrate the real-time signal processing is that as the USRP SDR is receiving the signals, it's passing them on to GNU Radio to be processed and to extract like the relevant data. And then that data is going to be sent back to our website backend to be displayed on our graphical user interface. This is just what our graphical user interface currently looks like. As you can see, there's a map that displays the trajectory of the satellite. The blue marker that you see is where our ground station is. The white icon that you see is like the satellite in question. It displays like the outputs that I was talking about, latitude, longitude, azimuth. That's all being updated in real time, as well as the future passes. If the user wanted to track another satellite, they would simply click on the button that says Add Satellite, enter the new catalog number, and they would be able to. Yeah, future work, like I said, we want to integrate the real-time signal processing into this workflow of our website application, and then integrate that into our graphical user interface. Thank you all for your time.
Thank you. All right. Stay on stage. I'm sure we have some questions. Or do we not? Wait, there's one at the back. All right, Mark.
Curious if you were able to leverage any like code or hardware designs from the SatNogs community.
We have been looking at those. They've been helpful resources for us to look at, but I couldn't say like any specific. Kind of just been taking things from everywhere and putting them together.
Anyone else? Okay, I have another question. I know you said this at the beginning, but you know it's like Friday, so my brain is getting a bit slow. So how does this? So you said you were a graduate student, right?
I'm an undergraduate.
An undergraduate student. Wow. So how does and this is basically what, like this project ties directly into your degree. And that's really cool. I feel maybe I went to the wrong school or something. But that is really impressive. I think this looks pretty cool. Yeah, one more round of applause, please, for Adriana. And